All right, so welcome. So I've reformatted the Canvas pages a little bit. So it should now look like this on the front page. So it has the layout of the lectures for the semester and then each of the weekly modules. So it does have the extra course introduction, but then the weekly modules, and they'll be increased as I get those reformatted too. So on each of these, underneath the units themselves, you'll be able to see the week material, and then, for example, this week's material has the homework, which is due Thursday, and then the assignment that's due Thursday, and then you'll also have the course orientation quizzes due this Thursday. And then there will be a link hopefully by tonight for Friday's quiz. It will open up at midnight Thursday night, and then, or Friday morning, whichever one you want to look at it, and then end at midnight Friday night. So it'll be open all day. You can take it at your convenience during that day, but it will only be open for the day only. So do make sure that you do take the quiz on Friday to get those points. All right, questions? Yes?
On the quiz for Friday, is it just over the material we went over this week?
So it will be up to the homework. So it will be KCL, KVL, and then power, Ohm's law, and then equivalent resistances. So it won't contain this lecture. It will be up to last lecture. Okay? All right, so expect a problem pretty much from each of those: a voltage question, a current question, power, Ohm's law, and then the equivalent resistance. So there'll be simpler circuits, hopefully, so you can do them in the allotted time. It will be timed, so once you start the quiz, make sure before you start it, you have materials. It's open book, open notes, and then make sure that you have a way to upload your work, and make sure to upload your work, even if you're like, I know I'm right. Make sure you upload those, else you cannot get any partial points. So if you do not upload any work, you won't get any partial points. If you upload work, you may get partial points. If you made a sign error or some other smaller error, you'll get those points. So make sure to upload your work, and that you are ready to upload your work before you take the quiz. Otherwise, it will take too much time and you may run out of time. Okay, so 45 minutes will be the quiz allotment time. Most of the time, it won't take you that 45 minutes, but do allocate enough time to take it. Right. Any other questions? Okay, you guys clear on what's expected this week? Okay, so homework, assignment, course orientation Thursday, or by Thursday. They're open now, so you can do them at any time. And then Friday will be the quiz. And again, quiz is only available the one day. Okay. All right, and then again, for the handouts and lectures, it has this table in here, so you can go to the handouts and lectures module, find the lecture notes without annotations, with the annotations from class, and then the video that's on there. All right. Okay, so we're gonna do, I was gonna upload the problems that we didn't get to last time, but I decided it might be worthwhile to actually work on them in here. So we're gonna go through those, and then we'll move on to the voltage divider today. So from before, we went over KVL, KCL, Ohm's law. So those are the three laws that are gonna give us our equations that we may need to be able to solve a circuit. So those are the three techniques, three laws that will help generate the equation set to be able to solve them. We also went over nodes, ordinary nodes. So ordinary nodes, extraordinary nodes, branches. What are the things that you remember about branches? Correct. Only one current. Okay. Yes. Multiple voltages. Correct. Anyone else have?
In between extraordinary nodes.
Correct. Extraordinary nodes. Great. Loops, we also went over, and a loop is closed loop, meaning that you have just one pathway from one point back to that point. So those were some of the terminology that we learned. So this is more terminology. All right, and then we also went over calculating power, calculating equivalent resistances, so finding an equivalent resistance between an A and B node. And then today, as I said, we're going to review some of those and then go on to the new topic of voltage dividers. So with this one, we want to determine the currents I1 to I4. Up there. So if you are sitting next to a new person, don't know your neighbor, do introduce yourselves to your neighbors, and then go ahead and work on this, trying to find I1 through I4.
You're Emma, right? Anna. I'm so sorry. Yeah.
So that would be an extraordinary one. So what would be that?
I'm just like, what the heck is going on with the batteries? Whatever. Like I
And then you can subtract that from what you're making. So it's 4S, now you have 2 volts. So you go across by 2 and 2. I agree last just because it's more complicated with the 5-volt battery. But I2 then is basically you have 12 volts going over 3 and 3 volts going over 6 volts. I might be wrong. They added up nicely, but I might be so bad. But that's how I started.
That would be a great way to find.
So 9 over 6 instead of 8 over 6. Actually, that's better.
So that one you can't do because you don't know what you're doing. Because you have in parallel, you have parallel branch to the parallel the resistance across that from the left to the right is going to be you don't know what it is. You're correct this one, it's not valid to say that the equivalent resistance between here and there by 1 is going to be 10 ohms. It actually won't. So instead you can do similarly to what you did so in the right one you don't know what I3 is. So then you would need to do the KCL and then that would give you, so you have 3 equations, 3 unknowns actually. And then if you add in the bottom one, you have 4 unknowns. So yes, you have the first 4 amps. And then you got 5 amps. There you can find, and you know the voltage at the top of the and find the voltage at the bottom right. As you use the left wire to label that, and 0 down from 0 down.
I just found out this morning.
And then you can find, you also know the voltage at the top of the right. So you can use the same idea. You have to make sure that you label that.
Cartilage or ligament, but you have a fracture. So the small bone that comes up to the top of the knee, I got a fracture on the top of the like my surgical program. And my surgical consult is until the 3rd week of May. I shouldn't have it, but
That could be that loop. And then just making sure you write the loop and then the and make sure your polarity is and then that will leave just want to know that their voltage across 8
yeah, you just have to keep up something. So yeah. Not very good.
Okay, that stopped presenting, I guess. Okay. Okay, a few different answers. So let's go through this. So I typically like to tell students, as you're starting this, you're like, where do I even start? I'm assuming some of you, I had that question as I went around, like, where do I even start with this? So you always want to identify what you are trying to find. In this case, we're trying to find I1, I2, I3, and I4. After you identify what you're trying to find, then you're going to try to write equations that contain what you are trying to find. So in this case, we were trying to find I1, I2, I3, and I4. So to write an equation, we use what information we know so far. So KCL, KVL, and Ohm's law. So those are what you're going to use to write the equations. All right, so before we also try and do that, we also need to highlight nodes, identify loops. So I'm going to highlight all the nodes. And to highlight them, that means between each element. So I have to identify the elements first if I haven't yet. So I identify the elements. If you need to, circle all the elements first. So these would be my elements. And then after I've identified the elements, I'm going to highlight the wires in between each of the elements. And each of those is going to be a node. So the node is a wire between elements. So the green, oh, I have two greens. What did I not use? kind of similar but different. Okay, so green node is ordinary, extraordinary. Ordinary, blue is, red is, purple is, oh wait, I guess those are hard to tell. Let's see, I'll do one yellow. Okay, I'll do this one yellow. Okay, yellow one is, correct, and the purple one is, correct. So now I need to know, like, I guess this would be identify branches and loops. So we've highlighted all the nodes, identified what the nodes are. So identify node type. Now to identify a branch, that means it's going to be between two extraordinary nodes. So a branch here would be, find something that's between two extraordinary nodes. So starting just from the left, that means that's a branch because it goes from the top extraordinary node to the bottom extraordinary node. This would be a branch. This would be a branch. This would be a branch. And this would be a branch. And then as you see from those branches, there's already a labeled current in each one of those. So in the first one, we know it on the left, 4 amps. Second one was I1. The third one was I4, and then I2 and I3. So each one of those already has a current in each branch. If not, I would want to put in a variable saying there is an unknown current in that branch. So that identified the branches, and now we need to identify loops. So there are several possibilities of loops. A loop is going through branches from one point back to the other. So that would be one loop. There would also be a loop going through here. There would also be a loop going around the whole outside. There would be a loop in the middle. There could be a loop going around that way. And then there could be a loop going that way. So lots of possibilities of loops. So extraordinary nodes is where we're going to write the KCL equations. So we have 3 options because there's 3 extraordinary nodes in here. So now writing the equation. How do we write those equations? So I'm going to start with a summation of current, which is my KCL. I'm going to label this one node 1. And I'm going to start with that one. So writing an equation for node 1, it's going to be the summation of the currents going in equals the summation of the currents going out. Or as mentioned before, you can pick the other 2 ways of defining that. Currents going in are plus, currents going out negative equals 0, or the opposite, currents going in is negative, currents going out is positive. I'm going to do the one where they equal each other. So going into this node is going to be KCL for current. So you're going to know that you need to sum currents up. So current, identifying that as 4 amps goes in, then I1, I2, I3 go out from that. So this would be 4 is equal to I1 plus I2 plus I3. If I label this one down here node 2, my current summation here will be that I notice that the 4 amp, even though it's labeled at the top, remember that it's going through all of this branch. And so in the node at the bottom, it's going to be a 4 amp going out of it. So that will be going out. Coming in, that I1 that's here is the same thing. It goes through the whole branch, so it goes into node 2. So I1 goes in. And then I4, same thing, it goes through the 1 volt into node 2. So into it, I4 equals 4. This node here, I'm going to label node 3. And, yeah, sorry.
Where did you get the 4 value? I see the I1 plus I4. On,
That's one branch, so that.
all they have the same current. Okay. Okay.
You got it? Okay. So yes, they're all the same current there. So node 3, it's going to be I4 going out. Looking. I4 goes out, I2 goes in, and I3 goes in. And again, I3 goes around the corner through this into node 3. So going in is I2 and I3, and going out is I4. So those would be my KCL equation set. So I have how many unknowns? How many equations do I need? So you have to have as many equations as you have unknowns, and possibly even more. So a minimum of that amount. So if I have 4 unknowns, I'm going to need at least 3, or at least 4 equations. So this is only 3. So what's my other possibility? Yes, or a question?
Oh, it wasn't a question. It was-
Okay, go ahead.
Yes.
Thank you.
Using KVL for the top left triangle loop, since you have all of the information needed to find the I1.
Okay, so taking a loop through elements that have the most known information is going to be what you're aiming for. So as Cole mentioned, that's going to be going through the 5 volt and the 1 volt, which is like my outside loop. So again, that was going to be this loop that goes through all of that. And depending on which way I want to go, I'm going to pick going in this direction. I'm going to label each resistance based on the current in that branch. So this is the current going through the 1 ohm. So what's my polarity? On the left? Or go ahead, Peter.
I was gonna ask, like, if, maybe you're about to do it, but I was wondering if you could set up a KVL equation for the outside loop.
Uh-huh. So these are the steps right before being able to take the full loop. So we need to identify the voltage going across each of the resistors. So the polarity for the 4 amp, what's on the left? Correct. And then the right? Negative. So remember, you just have to memorize that the negative means the arrow side. So the negative is always with that arrow side. Yes.
When you assign the polarity, do you always go with the current?
Correct.
Whatever.
Yeah. So I'm going to pick the polarity of that, and then I can label this. I would use the same polarity. I could call it V1 if I wanted to. But I would do it as the same polarity because then my Ohm's law is going to be positive. So V will be equal to a positive I times R. If I do it opposite polarity, I have to know in my mind I have to do a negative. It's just an extra step. So I always say do it the same way. All right, then we also need to know this one, and I just draw the current the same direction as it is in the branch. So what's the polarity on this one? On the left?
Positive.
Positive on the right?
Negative.
Okay. And again, I could label this as V2 if I wanted. And I could say that V1 is equal to Ohm's law. So 1 times 4 for 4 volts. I can then also say V2 is 8 times I3. Or I can skip the step of writing Ohm's law. So as you get more comfortable writing the voltage loops, you won't need to write that down, but for now I would say write that down. So now I also want to make sure I'm circling all of the correct signs. So as I start with my pen or pencil, I'm going to circle each sign as I go through the element. So here would be a plus, this one would be a minus, this is going to be a minus and a minus. And then this one would be a plus. So my KVL is going to be plus 12 minus 4 volts minus 8I3 minus 5 plus 1 equals 0. And since that has the most known information in it, I can also see as I write that it only has one unknown. So it's going to be easier to solve for I3. So I3 is going to be 4 divided by 8, so 1/2 or 0.5 amps. Plus 3 plus 1, 4, yeah. So this is actually 8, 8I3 is equal to 4, and then I just divide it by the 8 to get the 1/2. So now that I have I3, I can see if I can solve any of the other current equations, which I can't quite yet because I have still another unknown in each of those with I3. So what else could I do?
You could just do the top left triangle instead of the whole circuit or the outside circuit loop for KVL as well and get I1, which would allow you to solve for I4.
Okay. So I could do this loop just right there. And so with that one, I then need to label the I1 branch with a voltage. So I again know that this is going this way of I1, and it's plus to minus. So the voltage across it's going to be plus to minus, and I could label it V3. And so V3 is going to be 4I1. So my loop is going to be, if I start in the same left-hand corner, I go through the 12, through the 1 ohm, and then I'm going to go through that one, and it will be a minus there. So plus 12 minus 4 volts minus V3, which is also a minus 4I1. So plus 12 minus 4 volts minus 4I1 equals 0. So now solving this, I have 4I1 is equal to 8. And so this will be 2 amps. And I see having I3 and I1, this equation will give me, I1 and I3, then this one will have just one unknown. So I could substitute in, so 4 is equal to, I1 was 2, I2 is unknown, and then a 0.5. So therefore, I2 is going to equal minus 1.5 amps. 4 minus 2 is 2, minus 0.5, okay, plus 1.5. And then with I2, I can solve I2 and I3, I can now solve this one for I4. And that's going to be the summation of I2 and I3, which is I2 is 1.5, and I3 is 0.5 for 2 amps. So 1, 2, 3, 4. So that gives me all of the currents. Okay, questions? Yes.
So how did you get for I1? Because you were solving for I1.
So I know 4 amps. Do you see that there's 4 amps going through there? Okay, you know 4 amps is going through it. So I use the I times R. I is 4 amps, and then the R is 1 ohm.
Oh, okay.
So 4 times 1 is 4 volts.
Okay.
But you know it's 4 amps just because it was given to you.
Okay.
Otherwise, you would have to treat that as an unknown and take more voltage loops if it wasn't given to you. Does that make sense?
So you just used Ohm's law then?
I used Ohm's law.
Okay.
So yeah, I used that Ohm's law there. All right, was there another question? Yes.
Yeah, two. So the direction of current we just assumed off the given current, correct?
Correct.
And then for when you use KVL, since the 5-volt battery polarity switch, it basically acts as a voltage drop. When you do the outer loop with KVL.
So it just depends on how that's set up. So it is set up to have the plus on the top and the negative on the bottom. So as you are taking your loop, I started clockwise, but you could go counterclockwise and your signs would be opposite. So you would have a -1, +5, just depending on which orientation you're taking.
That makes sense.
So you just be consistent. If I start in that left, I'm going to go back to that left. So also, if I've labeled that as my starting point, I'm going to set that equal to my 0 volts. So everything is then going to be referenced as 0 volts from that point. So with that orientation of 0, then it goes an increase of 12 volts from negative to positive.
Right.
Does that help?
Yeah.
Okay.
So why is the 1-volt source positive, like the polarity positive?
So again, it's just a battery, and I could have it could have been built differently. So the reason you take the positive value in your loop, though, is because I started at 0 and then I went in this direction in a clockwise direction. As I go through that, I'm circling always the second sign I go through or out of the element. So +12, -4, -8 I3, -5, +1. So I have to always be consistent of I'm taking that second sign as I exit out of the element. Is that more clear?
Yeah.
Okay. Other questions? Yes.
I'm not sure if they just asked this, but the 5-volt battery on that right side,
Uh-huh.
why is that a voltage drop? Just because of the way it's oriented?
Mm-hmm.
So if you like flip a battery around, it acts as like a resistor almost?
Well, it's going to just, so instead of having a drop, it would supply.
Well, in this situation, it's dropping though, right?
Correct, because of the orientation, it's dropping. But if you flip it and the polarity's on a negative to positive, you would add it into the equation. So if you flipped it around to be in this orientation, you would have a plus of that.
So it just like acts like a resistor?
It doesn't act like a resistor, it's already generating its own voltage. I don't know if that answered your question or not. All right, in the back first.
So I guess to determine whether it adds or subtracts voltage, you just look at the direction of which you're going, and then it's the sign that's like exiting.
Yes, correct. That's another way of putting it. Yes.
For just determining the polarity of the resistor, it's kind of based on like, you said it's a starting point.
Yes.
If you start at 12, it's obviously going to want to decrease, but if you start at 0 and it rises to 12, it's still going to want to decrease. So you just set as the polarity that will decrease the voltage to whatever the starting point was.
So again, it's your perspective. So if I go to the right instead of to the left, let's write that one. So let's say I go through this loop. And in this time, I'm actually gonna go in this direction. If I do that, then I'm gonna have a minus here, plus here, and a minus here. So a -1, plus 5, plus 8I3, minus 4I1. So it depends on which way I choose to go around the loops, whether you view that as a increase or decrease. Is that help? Okay, another question.
Like just numerically, how would I solve a thing and get a current that has a negative sign? Like, how does that work?
So it's going to depend on your voltage orientations in the loops. So if you have more, okay, so if I have this orientation and the voltage difference there is going to be what? Voltage difference would be from the left to the right because I have the plus to minus. So 10 minus 8 over, let me put 1K to make it easier. So this is going to be 2 milliamps, and that would be a plus, right? Okay. If I have instead, the orientation is opposite, and I have 10 volts here. Okay. And I orient this current, I'll call it IX. Then this is going to be, I is going to be 8 minus 10 over, I'll do 1K again, over the 1K. And this will be a negative 2 milliamps. So depending on what orientation of your voltages are on the sides of the resistors, basically, we'll set those voltages. And that will determine which direction the current's actually going to flow. Does that help clarify that a little bit more? Okay. All right. Any other questions on this? We ran out of time. We did not get to voltage dividers yet. So I will go over the rest of this review and we'll start voltage dividers and current dividers next time.
Just to reassure myself, dealing with the KVL, do